Hi, Nicole. Can you hear me, Nicole?
Can.
Okay, good. Now, wait, you were one of the people that did didn't you do the simulation lab?
For which one?
For the equilibrium.
I might have.
Because you didn't have to do that.
There was one thing that it wasn't in the modules, but it was in the grade book. So I did just in case because I was bored and didn't have anything else to do. But
you're bored in a summer term?
It was like late at night and my parents went to bed and I didn't want to go to bed yet. So I thought I'd do it just to make sure.
You know, honestly, what I'm probably going to end up doing is making that an extra credit assignment anyway.
Perfect.
Because literally, Nicole, it's not you guys that are showing up at these meetings. You fairly know what you have to do and don't have to do.
Right.
People that are not showing up for the meetings, they're not viewing the videos, they're not reading the announcements, because I clearly stated in the announcements that you had to do the things that were in the modules.
Yeah.
What can I say?
I know the course shell is a little confusing, but
what's that?
The course shell itself, I feel like, is a little confusing. At least it's like not like my other classes, but it's
Nicole, there's a reason for that.
Yeah.
The reason is this was put together at the last minute. The guy that put this course together literally had to, it was told at the last minute, you have to get a simulation lab, and there were none for Chem 2. So what he did was he pieced things together, and as a consequence, piecing things together, it's just this jumbled mess. And if you think it's bad from your perspective, think about me.
I'm sure.
I literally been pulling my hair out this entire semester.
Yeah, and I can imagine.
All I can do is sit and apologize and tell you that you're smart enough, you're going to get through this. Hi, Jordan.
Hello, good morning.
Did you do the simulation?
No, I did.
You just do the stuff in the module?
Yeah.
That's what you were supposed to do.
I did it through like Canvas. I printed out the sheet and like filled it out.
That's what you were supposed to do.
Okay.
I don't know why I put it in the announcements. I've been telling you guys all along, look at the modules to do your stuff. But some people did the simulation thing and not the module thing, which what can I do? Either of you have any questions about what's going on in the lecture and the test?
I just wondered where to get the recordings of the Zoom meetings. Okay. I wasn't able to make them last week.
Is that for the lecture or for the lab or both?
For what you're doing now.
Okay. I am just about to share my screen. Okay. You see my screen, Nicole?
Yes.
Okay. It's really easy. It's the very bottom of the course shell. Okay, I'm going all the way down. You see Zoom meetings?
Yes.
If you click on this, what will happen is a Word document will print up, and you can click on the links.
Okay, awesome. I was going through all the tabs and I was so confused. I don't know why I didn't think to scroll all the way down.
Yeah, it's been there the whole time, and there have been occasions I've been like a day or two off, but for the most part, you can see right now I'm up to date.
Okay, awesome. Thank you.
Okay. Either of you have any questions? 1 second, I need to get Jolene is in. Good. Hi, Jolene. Oh, she's still connecting. Any questions about the test and what was going on with the test? You guys good about your scores?
What test? I just joined. I didn't hear it.
Jolene, are you in my lecture, Jolene?
No.
Then don't worry about it. Nicole and Jordan, are you okay with the test? Are you okay with the regrading and everything?
I'm only taking the lab.
There we go. Okay, Jordan, it's up to you.
Yeah, I'm good with it.
Okay. All right. Do you want to get started? And it's 8:06. Do you want to get started, or do you have any questions about anything?
The second lab that we did, I started doing it and I watched your video, but I was at the hospital with my dad all day and all weekend actually. And so by the time I got home, it was too late to call you. And I tried watching your video and Dr. Lou's video. But when I printed the lab, there were like 3 or 4 different pages of different charts to fill out. So I think I got through the first page okay. I made the Excel sheet, of course, okay. And I think the first E value was the slope, was what you were trying to say, and then you divide it. And I went through and I got my...
Go ahead.
I went through and I got my data from my lecture or whatever. Everybody has their own data. But then when you went through it, it just kind of didn't make sense to me.
Okay.
And when you explained it, I listened to it, you know, I don't know.
What I'll do is I'm going to go through that after this.
I'll show you what I have and you just tell me if it's right.
Okay. I will.
Because I'm embarrassed to turn it in if it's not mathematically sound.
Jolene, I will go through that with you after I talk about this lecture, okay?
Okay.
Yeah, fair enough?
Fair enough.
Okay. All right, guys, we good? Okay, this actually is a very, very simple concept, but there are some funky things about the concept that you have to understand. Are you seeing the, what am I doing here? Oh, that's what I'm doing. Yeah. Okay. All right, LeChatlier. Basically, the principle is if you have an equilibrium, okay, we got things that are very happy, they're going back and forth, everything is happy. Now, if you disturb that equilibrium, the equilibrium is going to react. The reaction is going to react such that the equilibrium gets reestablished. Do any of the 3 of you have a little brother?
I'm the baby.
No,
but I have 4 kids.
You have 4 kids?
So I get it.
Okay, so look at the youngest one, right? Jolene?
Yeah.
Do your 4 kids tend to stay in one spot?
Yeah.
No, literally speaking, if one comes in, it's kind of like the back seat of the car.
Yeah.
They try and get as far away from everybody else as possible. Does that make sense to you? Here's a little trick. And it's harder to work with people of Chinese descent and Indian descent because culturally they are almost on top of each other whenever they go anywhere. Okay. But if you are in like a room with somebody you don't know, just as an experiment, go up to them, walk straight up to them and almost be toe to toe with them. See what their reaction is. Generally speaking, what will happen is they will move away from you. The other thing is if you're talking with somebody you don't know and you move away from them, generally speaking, if you do it gradually enough, you're going to find that you kind of draw them along. And that's the basic kind of thing that we're talking about here. And that is that whenever you are at a position that is established, if you change that position, you are going to have to counterbalance that. Whatever is happening, whatever situation it is, counterbalances that and reacts in order to reestablish that equilibrium. Does that make sense, guys? Shake your heads. If
Yeah.
we're, all right. Jennifer, I want to speak to you after class, okay? Nothing major.
Okay.
Okay, now, what we can manipulate in a chemical equation are either the concentrations of the stuff we're dealing with, the temperature of the reaction, or the pressure / volume of the reaction. That's what we have to work with. Okay, so translated, guys. If we're dealing with concentrations, if I take something away, what happens is the system is going to shift in such a way as to replace what you've taken away. If you add something, the system's going to shift in a way to use up what you've added. Again, does this make sense? Okay. Jordan, you're with me. Jen and Jennifer, you're with me in lecture. Jolene and Nicole. Do you remember what Q is?
Heat.
No, that other Q. When we're dealing with equilibriums.
It's 5 years ago.
Nicole? Can't remember
Kinda.
things from 5 years ago?
I have 4 kids.
That's right. You can't remember what happened yesterday.
I don't know what I ate for breakfast, okay?
Okay. All right. If you throw concentrations into a reaction vessel and you do the numerical analysis, just like you would a equilibrium concentration or an equilibrium constant. In other words, you put the concentration of the products over the concentration of the reactants. Nicole, do you know what I'm talking about? Jolene, is this?
Yeah,
is this
concentration.
kind of
Just tell me, I'm a mathematician. I can go for it.
okay.
Concentration of the product over the concentration of the what? Reactant?
Of the reactants. Okay. Remember, all we've done is we've just thrown these things into a reaction. They're not at equilibrium.
Okay.
All right. If you have too many products, let me explain something else first. If you are at equilibrium, the concentration of the products over the concentration of the reactants adds up to a constant called Kc.
Okay, this is familiar.
All right. Now, if you're not at equilibrium, if you do that same calculation, then what happens is you get a number that's either higher than Kc or lower than Kc.
Yeah.
So, for example, you are higher than Kc. Jolene, if you're higher than Kc, if your Q value is higher than Kc, do you have too many products or do you have too many reactants?
Products.
So you have to do something to get rid of those products to bring yourself down.
More reactants and you would get rid of the products.
You could add more reactants, or more than likely what happens is the products are going to react to make the reactants.
Just wait a few more minutes.
Just wait a few minutes. The products will react to
Nicole
make the
keeps
reactants.
laughing at me. Am I funny? She's dying. I love it. You got a pretty smile.
Thank you.
Now that you've just usurped my class, Jolene.
I'm sorry. You want me to hit the mute button?
No, that's fine. Please don't. It's 8 o'clock. We need humor. Okay, so in order to get the Q equal to the K, if Q is too high, we've got to lower the number. The way we lower the number is get rid of some products. The way we get rid of products is we increase the rate of products going back to reactants. So not only does that lessen the products, that increases the reactants. And that is what makes the Q go towards Kc. Does that make sense, guys? Does that make sense? Give me a nod, a thumbs up. Thank you, Nicole. All right. Now, on the other hand, if I've got too many reactants, then I've got my denominator is too big. So if I've got too many reactants, I got to use up those reactants and make products. So if my Q is too low, that means my reaction shifts from the left to the right. Is what I'm saying making sense, guys? If you're a numbers person, LeChatlier can be explained by the difference of Q and Kc. If you're not a numbers person, all you got to do is just look at what is happening. You have a reaction. A plus B yields C plus D. If you have too much A, you got to think, A is too big. So we're going to make A too big here. We're going to go and show. We're going to make A too big. A is too big, right? So if A is too big, we have to work it so that we get rid of some A in order to get the equilibrium again. So what happens is, in order to get rid of A, the reaction shifts forward or it shifts right. Does that make sense? Make sense? Okay, we're going to put A back to normal. Now, if we add more C, got a lot more C in there, okay? If we add more C, we got to get the reaction back to its normal. So in this case, when we add more C, the reaction is going to shift to the left or in the reverse direction to get rid of C.
Kids getting away from kids.
I'm sorry? Yes, exactly. You're stressed out, so you got to get away from the kids, Jolene.
Yeah, kids getting away. I have a notation question. Is this a big Q or baby Q?
Big Q.
Okay.
Big Q. Small q is generally energy. Okay. So we have, if we are adding more, then we are having to get rid of it by shifting it in the opposite direction. Okay. Now, what happens if I take away B?
It's going to shift left.
Wait, what happened to it? Yeah, there it is.
Shift left.
There's B. So we're going to have to replace the B. So we are going to shift it left.
Yeah.
And when we shift it left, we get back to our equilibrium again. Same thing. If I take away D, maybe it's too small. Then what is going to happen, Jordan?
Wouldn't it shift to the right?
Because we've taken away D, so our reaction is going to shift to the right. And when it shifts to the right, we reestablish our equilibrium and everything's happy again.
Mm-hmm.
All right, are you good with this concept, guys? We good? Do we kind of understand this concept? If we put in more of one thing, then what's going to happen is the equilibrium is going to shift to the opposite side. If we take away something, the equilibrium is going to be shifted such that things get pulled towards it. Does that make sense to you all?
Mm-hmm.
All right. Now, let's think about pressure for a second. Now, pressure is equal to force, and pressure is nothing more than the force per square surface area. That's what pressure is. So in order to increase pressure, pressure is equal to force over area, and force is equal to the number of particles times the mass of the particles times the acceleration of the particles. So can you all see if you have more pressure, you have more particles hitting the sides of the container. Does that make sense, guys? So my pressure is directly related to the number of particles I have. Does this make sense, guys? Thumbs up. If it's not making sense, I need to know that now. Okay. So if I'm looking at a chemical reaction, if I'm thinking about this particular reaction on a molecular level, I have 3 molecules of hydrogen reacting with 1 molecule of N2 to make 2 molecules of NH3. Which side has more molecules? Which side has more particles? The left or the right?
The left.
The left does. So if I add more pressure, adding more pressure means that I have put particles in there, right? Which way is this reaction going to go to make less particles? Is it going to go to the right or is it going to go to the left?
To the right.
Because we're going from 4 particles to 2.
Following the gradient.
So that is basically, if I add more pressure to this reaction, I'm making more NH3. And think about it. If my goal is to make ammonia, am I going to want to do this under low pressure conditions or high pressure conditions?
Low.
If I do it under low, Jolene, then I have to make more particles. I have to make more particles to make up for the pressure loss.
So high.
So I want to, if I want a high pressure, the high pressure forces it to go into the shifting right, which means we're in the forward direction. I'm making more ammonia. That's basically what chem engineers do.
Got you. I see it now.
They look at a reaction and they determine, oh, my reaction's in equilibrium. Okay, I can make so much ammonia. How can I make percentage-wise more ammonia? Well, I've got 4 particles on the right, on the left here, 2 on the right. So if I know the pressure is related to the number of particles, if I put more pressure in here, my reaction is going to want to relieve that pressure. One of the ways that the reaction can relieve that pressure is to make less particles itself. So it's going to shift in the right direction. If I take pressure away, which way is it going to shift?
To the left.
Because I want to make up for that loss of pressure. The way I make up for that loss of pressure is to create more particles.
But it would be unstable, correct?
No, it would be in equilibrium.
It would still be at equilibrium after you do low pressure?
Yeah, but the difference is, Jolene, my KC will be changed.
So it would not be at equilibrium.
Yes, it would be at
the KC would change. Got you.
KC would change. That means that my proportion of my products and reactants are changing. It would be at equilibrium, but just a different equilibrium.
So you've changed, you had a chemical reaction.
Yes.
Okay. I'll buy it.
Okay. Now, let's think about this in another way. How does volume affect pressure? Boyle's law, guys. How does volume affect pressure? Squeeze a balloon, guys.
M1 V1 equals M2 V2.
I'm sorry, what?
M1 V1 equals M2 V2.
That is the concentration equation. It's not M1.
It's the same concept.
Same concept. It's P1 V1 equal P2 V2.
There you go.
When you squeeze a balloon, you make the volume smaller. What happens to the pressure?
Gets more increased.
So if I decrease the volume of my reaction up here,
you're going to increase the pressure.
And so which side does it go to?
it's going to go to the right.
Exactly.
Whew.
Jordan, if I increase the volume, which way is the reaction going to shift?
Well, it would decrease. So would it go towards the right because it's a smaller number?
No. Remember, you're decreasing the pressure. You got that part right. You're
Okay.
decreasing the pressure. So what the reaction wants to do is it wants to make more particles to make up for that decrease in pressure.
Okay, so it would go left.
So it goes left.
Okay.
So you got to realize that what's happening with the pressure is the opposite thing that's happening with the volume. Increase the pressure. The reaction is going to move to the right because it wants to relieve that pressure. Increase the volume, pressure has gone down. Therefore, we want more particles, reaction shifts to the left. Are we all solid on this? We good on this? Pressure and volume is a harder concept to understand than temperature. Yeah, I just went through that and that. All right. The easy way. I lost somebody along the way. Who did I lose? Oh, I lost Jennifer. Okay. All right.
Here? I don't
Jennifer,
know.
you still here? I'm sorry.
I don't
You're-
know.
I've got 4 people, and basically somebody joined in and kicked you out. I got 4 panels here.
Oh, well, I'm still seeing your lecture and hearing you.
Okay. All right. Now, temperature is a little easier to think. If you can think of temperature as being a reactant or a product, it makes it a lot easier. Endothermic. Heat is absorbed. So you got to put heat in to make the reaction go. Are you all with me now? Endothermic, got to put heat in. So it becomes kind of like a reactant. If you need heat to make the reaction go, it's a reactant. So if I have an endothermic reaction, I'm putting heat into the reaction. I'm adding it to ammonia chloride and water. If I add more heat, that's kind of like adding more reactant, right? So if I'm adding more reactant, which way is the equilibrium shifting? Is it shifting to the right or to the left? Okay, let me ask it again. In this particular question, if I add more NH4Cl, does the reaction shift to the right or to the left?
Would it be right?
Because I'm adding more. It's shifting to take it away. It's shifting to take the NH4 away, so it's shifting to the right. All right? If I'm adding heat, I'm adding more reactant. Which way is that going to shift this equilibrium?
Left?
If it shifts it left, I'm adding more reactant. If it shifts it left, I'm adding more heat. Is that what I want to do here? Okay, let's go back. Let's go back to the original letters, if I can find them. All right. My original letters, okay? I have too much A. Right? Remember this? I have too much A. Which way does it shift the equilibrium, left or right?
Wouldn't it be right?
It goes to the right because I want to get rid of A. So think of A as being heat.
So change it to Q.
I'm sorry?
Put a baby Q.
Yes, baby Q. All right, but let's erase that from your thoughts right now, Jolene. Let's stay away from energy for a second, the concepts of energy, and just go with heat. Okay. If I'm saying that heat is a reactant,
Yeah.
just like A, if I add more heat to this reaction, which way am I going to shift the equilibrium? Is it going to go to the right to take away heat, or is it going to go to the left to make more heat?
Right.
It wants to get rid of the heat, so the reaction is going to go to the right. Same concept. If I have, oh, that's a little too small. If I have my reaction, if I've taken heat away from my reaction, which way does the equilibrium shift to make up for that?
Wouldn't it be to the left?
It goes to the left, guys. So let's define this. First of all, when you've got a reaction, when you have a reaction, you have to, first of all, discover whether it's endothermic or exothermic. If they tell you it's endothermic, it goes on the right side. If they tell you that the delta H is positive, it goes, I'm sorry, excuse me. Let's erase that. If they tell you it's endothermic, it goes on the left side. Heat goes as a reactant on the left side. If they tell you that the reaction has a positive delta H, it goes on the left side. Now, if the heat is on the left side and I add more of it, I want to alleviate that extra heat, so it pushes the reaction to the right. If my reaction is endothermic and I take away heat, well, the equilibrium wants to get that heat back. So it shifts the equilibrium to the right to make more heat. Similarly, if I have an exothermic reaction, exothermic reactions release heat. Think of exothermic reactions as products. So if you're told it's an exothermic reaction, or if you're told you have a negative delta H, put heat on the right side of your equilibrium. Now, if you have too much heat, which way is the reaction going to go, Nicole? Nicole, are you adding more products or are you adding reactants?
Reactants.
I'm adding heat. Which side of the equation is the heat on?
Oh, yeah, no.
Products. Is the heat on the product side of this equation?
I don't know why I'm so confused right now.
Left side of the equation, reactants.
Yeah,
Right
so
side of the equation,
product.
products. So the heat is a product. If I add more heat, I want to take that heat away. I'm sorry, if I add more heat, the reaction wants to take that heat away. So which way does the reaction shift?
Left.
It goes to the left. It wants to get rid of the heat, so the reaction is going to shift to the left. If I take away heat, Jennifer, is heat a reactant or a product?
A reactant. I mean, heat is on the product side, but if you take away, it's going to be skewed to the right.
Exactly. Heat is a product. If I take it away, then the reaction is going to shift to the right. I'm sorry, I'm having a hard time understanding why you picked up on the concentration thing so readily, but you're having a hard time with the heat. You add Cl2, Jordan. You add Cl2. Which way is the reaction going to go?
Shift to the right.
If you add more heat, which ways the reaction go?
To the left. It stays right?
No. I was putting my hands up there like it's obvious.
Oh.
I was putting my hands up there because you answered it perfectly and it's obvious. Voila. Okay.
Okay.
Jolene, I have an endothermic reaction. I take away heat. Which way does it shift?
Endothermic reaction is going to shift to the left.
Going to shift to the left. Jennifer, endothermic reaction. I add heat. Which way is it going to shift?
To the right.
To the right. Okay. Adding heat. Just first of all, determine whether it's endothermic or exothermic. If it's endothermic, put it on the reactant side. If it's exothermic, put it on the product side. Then you have to determine whether you're adding or taking heat away, and just treat it like you do a reactant or a product. Okay? Now, I'm going to play with some things, okay? So this is Mr. Popovich ad-libbing. When Mr. Popovich ad-libs, things go sour sometimes, okay? I have a reaction. I have a small reaction. I want it to be a bigger reaction. I have NaClO4. With this, I am making NaCl aqueous plus O2 gas. And this is a solid. Okay. Now, if I tell you AgNO3 reacts with Cl minus to make AgCl solid. Okay? If I add AgNO3 to this reaction, what am I essentially doing?
Wait, I just spaced out. If you add what? AgNO3 to this reaction?
I just told you that AgNO3
Reacts
if
with Cl.
If it's in solution, will react with any chloride ion to make AgCl, and that's a solid.
It's going to break it up.
It's going to break what up?
The left side of your equation.
Which equation are we talking about?
The first one.
Talking about 1 or 2?
If we're at 1.
No.
You're going to add 1 to, you're going to add 2 to 1?
Okay.
Well,
1 is occurring. 1 is occurring. Okay. Reaction 1 is occurring. Now, to reaction 1, I'm going to add a solution of AgNO3.
Yes.
What is happening? First of all, how does this exist? NaCl in water.
Salt.
What exists is what? You put table salt in water. How does it exist in that water?
Breaks up, salt water.
Breaks up into its ions, right? Right? Yes. Why is this not cooperating with me? Okay, isn't that what's happening?
Yeah.
If I'm in solution, then my solid goes into Na plus and Cl minus. Salt, when it's in solution, exists as its ions, right? So I've got this equilibrium going. Now I want to play with it.
Got you.
So
It's
I'm
gonna
playing
shift
with
to the
it
left.
by adding silver nitrate to it.
Yeah.
What is happening? Is the
It's
silver nitrate affecting the first reaction any?
Will it take the chloride ion out as a solid?
Yeah. Breaks
It
it up.
takes the chloride ion out as a solid. What have you done to the first equilibrium then? Have you taken away a product? Guys, the silver is reacting with the chloride to make a solid. Is the chloride in solution anymore?
No.
So it's out of play. What have I done to the concentration of my chloride ion?
Absorbed it.
Have I increased it or decreased it?
Decrease.
If I've decreased it, which way does the reaction go? Does it shift to the left
To the
or
right.
does it shift to the right?
To the right.
Yeah.
It shifts to the right. So the simple act of putting silver chloride into my equilibrium, the silver ion reacts with the chloride ion to make silver chloride and takes the chloride ion out of solution. It depletes the concentration of the chloride. That means because I'm taking away chloride ions, I'm shifting my reaction to the right. Okay? I have lead ions. I have lead nitrate. Bad stuff. Horrible stuff. This stuff makes children, basically, it takes away their mental capacity. So if I have this in solution and I add water to it, I make lead ions. And I make nitrate ions. Does that make sense to you guys? Does that make sense? So if I have a side reaction, okay. Okay. In this case, this is going to be my first reaction. This is going to be my second reaction. Okay. Now, I have a situation. Say I'm in Flint, Michigan. And by the way, this is an equilibrium. This is not an equilibrium. This is an equilibrium. I have this in Flint, Michigan. I've got lead in my water, which effectively means I have lead ions in water, which means you can drink it and it gets distributed throughout your body readily. Bad stuff. Everybody knows lead is bad stuff. So I want to get it out. If I add OH minus, what's OH minus? Acid or a base? Is it an acid or a base, guys?
Is it a base?
I'm going to have base. Okay. So if I have my OH minus and I mix it with my lead, I can take the lead out of the solution. Now, what effect does that have on my original reaction? Which way is it shifting my original reaction?
I have a question.
Yes, I have an answer.
Would it shift to the right because you're taking away the lead?
Absolutely.
Basically, could you kind of interpret it as if it's on the opposite sides of the equation and it's the same, you could like cancel it out, basically like removing, and it would go to the right? Could you think
I'm not understanding what you're saying, Jennifer.
So like right now, the first equation.
This stupid look means I'm confused.
So this is how I'm thinking of it. So equation 1 or line 1, lead is on the right side, and then equation 2, lead is on the left side. So basically it's like removing each other. So could you think of it as it's being on the right, it's skewing to the right because it's
okay, I can buy that.
Could you think
I can buy that
for each problem? Basically, depending on like what side it is and stuff.
Yeah, because yes,
Okay.
You can think of it that way, Jennifer, because literally speaking, what I'm doing is I'm chewing up the lead ions by having them on the reactant side of a reaction that goes all the way in one direction. So I'm eating up lead ions. They have to come from somewhere. They're coming from the original equation, which is basically shifting this reaction to the right. Does that make sense to you guys? All right. What happens if I add HCl to my chemical reaction on top here? Which way is it going to shift the equilibrium?
To left.
It's going to go left because HCl is almost entirely making H plus ions plus Cl minus ions. So I put this into the original equation. I'm literally generating Cl minuses. I'm increasing the Cl minus concentration. So it makes this reaction go left. Is this kind of making a little sense, guys? Jolene, you just gave me a funny look.
I was scratching my back.
Oh.
I was trying to reach the middle.
Don't you have a child to do that for you?
They're all asleep except for the baby. They wouldn't do it. I have a bunch of teenagers. They hate me.
Now you have to understand, there's this concept of food for chores.
Yeah, we do that.
Yeah, well, I've never seen a child starve themselves yet. Okay, now, I could sit there. Do you want me to take you through the simulation? This is a different simulation using a different company. So the rules are a little bit different there. I'm going to stop this for a second. That's closed. Okay. Everybody seen the screen?
Yes.
In here. Okay. Again, this is not a McGraw-Hill. Not a McGraw-Hill laboratory. This is one in which you are going to have to print out the form and submit it in a report sheet. Not a McGraw-Hill lab. So if you click on the principal lab, it goes through a little bit of introduction. And talks about basically some of the things I've done. They get into more of the Q thing than I did. This is the reaction you're going to be working on. You have this compound that's blue, and you have this other compound that is red. What you're going to do is you're going to manipulate this equation such that you're going to turn it so that you can see it either shifting left to make the blue color or shifting right to make the red color. That's ultimately what you're doing here. You are going to play with this equilibrium, equation 2. You're going to play with that such that you either shift it right to make the red color or you're shifting it left to make the blue color. Okay, please watch the introductory video. That is going to tell you how to do the simulation. It's a little bit different than what you did for McGraw-Hill. You've already done the pre-lab, the report sheet. This is what you have to do. It's a fairly simple lab. You're going to do the simulation and you're going to make observations. Okay? You're going to add these things and make observations, whether the solution is blue or red. You're going to do that down here. Those are going to be your observations. And while you're doing the simulation, you're going to say how much you added of the volume, and you're going to be able to record what the molarity is for each one of these species and the temperature. Record that data after each one of these steps. You're going to have to go through some observations and how that affected your reaction. Observations after 50. Then you are going to, from the changing of the temperature from room temperature to 50, you're going to be able to tell whether the reaction is endothermic or exothermic. Then you are going to have to calculate Kc for the reaction at 50 degrees centigrade. It's not, this is not cooperating. Have I lost you guys? Have I seen, have you lost the screen yet?
No.
You're still seeing the report?
No,
I'm
seeing what you're, no, I'm seeing what you're doing.
Okay. That's fortunate. No, I need this. So I'm going to figure out what my equilibrium constant is going to be based upon the concentrations that I just submitted to you, that I just showed you. So this is my reaction, equation 2. That is my reaction. Water doesn't enter into the equation at all, ever. There's just too much of it out there. If I just have water, then you would basically have an infinite Kc. So what happens is the water gets incorporated into the equilibrium constant. So basically, I have, that's what would be this water. I have this compound, COCl2 dot hexahydrate. From the simulation, I'm going to find the concentration of this. I'm going to divide that by the concentration of my Cl minus. And that is going to be my Kc.
Can you say that one more time, please?
I'm going to take the concentration I find of my hydrate, and I'm going to divide that by, because there are two Cl's there, I'm going to divide it by the concentration of my Cl squared. Because an equilibrium concentration takes the concentration of the products and divide it by the concentration of my reactants.
Yeah.
So that is what I'm doing in these boxes. I'm recording the hydrate concentration and the COCl4 concentration and the Cl minus concentration. And I'm using those to do my K. Why did they? Okay. Guys, we're not using 2, we're using 5. That makes a lot more sense to me. We're using equation 5, not 2. So that when I'm getting my equilibrium constant, I'm taking my concentration of COCl4, 2 minus, over the concentration of my CO hexahydrate plus my chloride raised to the 4th power. Are we clear on that?
Yeah.
So we're clear on how to get these concentrations, right? We good? Anybody that's not clear, give me a thumbs down right now.
I have one question. Are we watching a video for this information?
No, you're doing a simulation.
And the simulation is in McGraw-Hill?
No,
I didn't think so. Where's the simulation at?
It's right in the thing. You go under procedure.
Got you.
Open the Chem Collective simulation.
Got you. Okay.
And hopefully this is going to load up for me. There we go. Okay, I'm going to get rid of this. Now, what you have to do is you have to take things from the stock room and put them on your workbench. So you also want the cobalt chloride experiment. So under that, I have 3 solutions. Go back to the stock room. Okay. Now, I also have to grab glassware. I have to decide whether I'm going to use pipettes. Okay, so I have all these things available to me. Okay. Now, I believe you're going to have to go through the print. I would print this out. All right. It tells you obtain a 250 flask, 50 milliliter grad cylinder, and disposable pipettes. So glassware, grad cylinder, 50 mils. And what else did it say?
Don't remember.
What use are you?
None.
How do you think I have you in here?
So watch me fail.
Okay. 250 Erlenmeyer.
Mm.
So print out that list, and you're going to have to figure out what you need. Nope, not a volumetric. Erlenmeyer.
Mm.
250. Okay. All right. Now, you're going to have to pull down what you want. Okay, if you notice, do you see this over in the left-hand side here? It's giving you what species you're dealing with and the molarity. So you're gonna have to pull this down, put it over the, again, it's a bit cumbersome and you gotta get used to it. Put it into your flask. Now, what's gonna happen is it's going to give you a chance to choose the volume. Okay, withdraw. I've taken it out of my Erlenmeyer flask. I now have to move this over. I have to take my pipette and drop it in. Again, it's futzy. So if I want to put 1 milliliter in, I go to the, I may have to do 10. I go into the pour and it goes from the pipette into the flask. Look at the video. They're going into much more detail than I have. Okay. Now, this is my reaction vessel. This is, I think I can just, I could take this and remove it. Oh, crap. Yes, I can see how frustrated you get with this. Believe me, I'm not a fan of it myself. So you can get rid of glassware by right-clicking on it, remove. So that pipette went away. Now this is my reaction flask. Okay, I can take this out of the way if I want to. Okay, right now, if I click on my reaction flask, I have molarities, correct, guys? If I go to my stock room and I get a five milliliter pipette, I could take my acid. I'm going to take my pipette, put it into the acid, and let's say I'm going to put 1 milliliter, withdraw. You're not going to see how much it is because it's not at the level. I'm now going to take my pipette, move it over into my flask. My reaction flask. 1 milliliter, pour. It's gone in there. Now you notice, because I put HCl in there, there's no more OH minus. And these concentrations are flicking up, okay? Wait till they get as steady as possible. Then record those concentrations. Are we confused at this at all? Again, please, the video is about 5 minutes. And basically what you're going to do is they tell you to keep on adding 1 milliliter intervals. This has got 5 in it. I can put in 1 more. Pour. Okay, it doesn't have enough volume. So I got to X out of this. I got to go get more. Withdraw. 5. Withdraw. Okay, put it in here. Pour. Did you notice the color of the solution? Color went kind of like a bluish thing, that's how you know you've added enough HCl, because it shifted it from the red to the blue. Any questions about this stuff? Okay. Make sure you're keeping up with your discussions. I haven't graded them yet, but there's going to be a time when I finally get some time on my hands, and I'm going to go through and grade the discussions, guys. So make sure you're keeping up with them, even though they haven't been graded yet. And all I'm going to do is specifically count to make sure that you have done your 3 comments per week. Okay, Nicole, Jordan, Jolene, and let's see, who else is in here? Vanessa, Keanu, Jenna, you're here, okay. Let me do that while I've got a chance. Jordan, you were here, Vanessa's here, Jolene, Jenna's here. Jennifer is here. Keanu is here. Anybody I miss? Okay, guys, that's all I have. Jenna, Keanu, Vanessa. Jennifer, I do want you to stay. Did you do for the equilibrium constant laboratory? Oh, Jolene, you had a question, didn't you?
Yeah, I have to go get my paper.
Okay. Vanessa, Keanu, Jenna, and Jennifer, did you do the McGraw-Hill simulation, or did you do the module? Or did you do both of them?
I did the
both.
modules.
You only had to do what was in the module. Okay?
Yeah,
Now,
I only did the modules.
you only did the module?
Yeah.
You're good.
Mm-hmm.
Keanu,
Okay.
Vanessa.
I did both.
Okay. I've got some possible good news for you. Keanu,
Yes.
what did you do? Did you do the module or did you do the McGraw-Hill simulation?
A
Or both?
module.
You did the module? Okay, you're fine. All right. If you did the simulation in the McGraw-Hill thing, I am thinking I'm going to look into it and I'm going to see whether or not I can use that as extra credit for you guys. Now, please, from now on, go to the module. The module will tell you which one you're doing. For example, even though the equilibrium was open in McGraw-Hill, even though it was open in there, you didn't have to do it. All you had to do was what was listed in the module. Go to the modules. It will tell you what you need to do. I also said this in the announcements, both June 6th announcements and the 13th. I told you that you had to go to the modules to do this. Thinking June 6th, I said Canvas. Are we okay with that now? Do we understand where you have to go to get your assignments? Anybody confused? Okay. That's all I've got for you guys. Unless you want to see Jolene talk about last week's experiment, then you're free to go.
You see my experiment?
I'm
So
sorry,
those are
Nicole?
What?
No, I'm sorry. I thought you had a question.
Oh,
Jolene,
no.
what you got?
Thank you.
You're welcome.
So this is my data that was given to me.
Okay.
And then
That
this
first
is,
one,
yeah.
first data is that the data from the individual experiments?
Yeah, like they gave me data B, so I
Okay.
wrote it down. And then I have my slope from my graph.
Okay, you got those. You got your slopes.
Now,
So
is my slope go right here in this thing? The E?
It is the funny looking E.
The element sign?
The epsilon.
Yeah, epsilon or element.
Okay, so
then I did exactly what you said, but how do you differentiate between these two? Because their equations are the same.
Okay,
Are these values the same?
I'm not exactly seeing what you're saying, so let me get into that, okay? Modules, where are modules at? There we go. Okay, so I've seen you put the individual trials in here.
Yes.
I've seen that you have gotten your slope and put it in there.
Yes.
Okay, now what you were supposed to do was you were supposed to add different amounts of SCN for each trial. The initial moles of Fe is going to be the same all the way across. Okay, Jolene?
Where did you find that information at?
Initial moles of, you have the concentration times the volume used.
Okay.
Okay. Your concentration is 2
and the volume
e
was
to the
10,
minus third, and the volume used was 5 milliliters,
5
right?
or 10. I thought, yeah, something to that.
No, it was 5 because this is the original concentration, right, Jolene?
Okay.
Jolene, you got that?
Yeah.
The 2 e to the minus third was the original concentration used.
Okay.
All right. You're multiplying that by the original volume, which was 5 milliliters.
Okay.
So that goes into the initial moles of Fe plus 3.
Okay.
Now, your moles of SCN, you have the same concentration, but in each test tube, you're adding a different amount, right?
Yeah.
You added 1 milliliter here, 2, 3, 4, and 5, correct?
Got you.
So you're doing this concentration for the test tube 1, you're doing this concentration times 1 milliliter of your SCN. Second column, this concentration times 2, this concentration times 3, 4, and 5. You got that now?
Mm-hmm.
All right. Now, to get the equilibrium concentration, you're going to take the absorbance. You got
divide it by the slope, right?
Right.
Okay, and that would be for the equilibrium on top.
That's the equilibrium of FeSCN.
And then the equilibrium of the
moles,
bottom.
Equilibrium moles
is times 10 divided by 1,000.
Yes.
Yeah, I got that part correct at least. I couldn't figure out this one. I was like, what am I doing wrong here? Okay.
And then for equilibrium moles of Fe, you're going to subtract initial moles of Fe.
You're going to subtract these two?
You're going to subtract initial moles, this one right here, and equilibrium moles of FeSCN.
Which my initial moles are all incorrect. So that's why my data was so all over the place. Okay.
All right.
Because I'm like, they're the same. Why would they be the same? Because I just filled the same for both boxes. Got it.
Okay. So you're understanding what's going on. You just made that one mistake.
And then I was like, there's no way that they would all be the same. That would be pointless for them. So I was embarrassed to turn it in.
Correct it and send it in. Can you finish it today sometime?
I could finish it in a half an hour.
Go ahead. And did you submit it yet or not?
No, I was too embarrassed. I was like, I know these calculations are wrong and I'm not going to send something in that's completely wrong.
Okay, so what I'm going to do is I'm going to hopefully.
I just email you. You want me to email you it?
I would rather have it in one place if I can.
Makes sense. So then the step 4, what are we doing?
Okay, I'm going to have to get back there. Okay. Oh, crap. Oh, I know what I need to do. This is what I need to do. And 5 p.m. okay?
Yeah. I appreciate it.
And Jolene, I know the time is hard for you. When did you come across the error?
Saturday and Sunday, but my dad, he made me stay with him at the hospital because he was all by himself. They take care of his mother-in-law, and so she's stuck at home babysitting my stepmom, and he's had partial foot amputation, but he's looking at getting the whole foot amputated. Diabetes, and he also has a liver kidney transplant, open heart surgery, cancer, because of the anti-rejection. So he's missing his chemo treatments. I mean, it's a mess, and he's just lonely and scared. Sorry for you. No, it's okay. I just wanted to spend valuable time with him, and he made me play chess the whole time. And I'm like, what about my homework? He's like, you'll do it. You'll be fine. And then I ran across the error. I was working through it, and I just kept working through it. And I said, I got to figure it out. I got to figure it out. Because usually I can. And I just couldn't figure out why my data was so skewed at the end. And I was like, I did something wrong. And I knew it was the first step, not the second. And I'm like, well, how do I figure the first step out? And it was just entirely too late to call you.
Why?
I'm not gonna.
What is too late, Jolene?